Nice. Okay, it's recording. All right. So, yeah, let's cover some other examples. I'm trying to scoot this a little forward. All right. So we were talking about. I got that one over there. Let's do another really quick. I've got 3y double prime minus 8y prime plus 3y. Now, I might have mentioned this to you or whoever was in Calc 3 in a previous semester that diifyq, at least this part of diifyq, is as easy as knowing how to factor a quadratic equation.
Okay.
So 3r squared minus 8r plus 3 equals 0. Can you factor this? Sure, I can factor that into. It takes a little bit of guesswork, but nothing we can't handle, especially because the only factors of 3 are 3 and a 1. Same over here, the only factors of 3 are 3 and a 1. So is there a glare? Yeah, it's kind of a glare. You have to live with it if you're watching at home, sorry. 3, let's say plus 1 minus 3. And that's how that factors. And then we know that r equals negative 1/3 and r equals 3. So that means your solution, based on these values of r, is going to be c1 e to the negative 1/3 t plus c2 e to the 3t. A lot of people give me the question, does it matter what order I write it? Does it have to be c1 with the negative 1/3? Does it have to be c2 with the 3? No, it doesn't matter. Those are just the way I wrote them in here, so that's the way I'm going to write them in my answer. No reason you have to write one first rather than the other. Cool. So that's when the roots are real and distinct.
So these are second order.
These are second order linear. This is in particular called homogeneous, which is confusing because you've actually seen this term before, right? You saw it with regards to the substitution method v equals y over x, right?
Mm-hmm.
You ever did a substitution v equals y over x? You did that for a type of equation where it was considered homogeneous. What's weird about that is that has nothing to do with this. So the term homogeneous, as it applied to first order linear differential equations where you had to do some sort of substitution, not relevant here. Okay. So that's they use the term twice. Very confusing because you think, okay, well, in what way am I going to be using that substitution? The answer is you're not. It has nothing to do with that. Very confusing. But in our case, homogeneous just means this right-hand side is 0. So that's all that means. When we talk about non-homogeneous differential equations, the right-hand side will be non-zero. Okay, there's an example over here for the people watching at home. You can pause the video, and there's the work for that one. This is a repeated root, 2r plus 3, 2r plus 3, so it factors accordingly, gives you a root of negative 3 halves, and if you see, the solution has an extra factor of t right there, t e to the negative 3 halves t. So that's important when you get a double root. And again, that's going to be a common theme, that whenever you get that double root, whenever you have a double root coming from some sort of factoring that you do, or you see some sort of match, which we'll get into later, then you have to throw in an extra factor of t, or x, as it might be for your case. Okay, and lastly, let's do one with complex roots. Y double prime plus 2y prime plus 5y equals 0. Try as you might, r squared plus 2r plus 5 will not factor. 2r plus 5 will not factor. No dice. So what we're going to try and do then is complete the square. So watch closely. Here's how you complete the square. Parentheses, put the r there, squared equals negative 5. I'm going to throw that 5 over to the right. I'm going to condense r squared plus 2r into a set of parentheses with r plus something here. What goes here?
4.
It's half that guy.
Oh.
Half of that coefficient, this is 2r, half that coefficient goes here, so that would be a plus 1. Make sure you keep the sign. If it was a minus 2, you'd say minus 1. This is a plus 2r, so you're going to say plus 1. All right? We're not quite done. What's 1 squared?
1.
So you can either subtract it from the left-hand side or add it to the right-hand side. I'm going to add it to the right-hand side just because if I subtract it from the left, I'm going to add it over anyway. So we have r plus 1 squared, and I'm going to actually... Hey, coming in. Doing good. That glare is like right in the way. It's kind of annoying. Oh well. It's not really conducive for recording, but alright. Anyway, r plus, so we take half that coefficient, half of 2 is 1, r plus 1 squared equals negative 5, and we have to add a factor of 1 over here. This comes from squaring whatever number's there and putting it over here. Okay, so we have r plus 1 squared equals negative 4. To solve for r, I'm going to take the square root of both sides. So I get r plus 1 equals plus or minus the square root of negative 4. What do you call the square root of negative 4?
2i.
You call it 2i. Then I'm going to subtract 1 from both sides, and this gives me r equals negative 1 plus or minus 2I. Now here's how you interpret complex conjugate roots as it pertains to a solution to a second-order linear homogeneous differential equation. Here's how you interpret that. The real part is just like it was for these guys over here. You're going to start by saying y equals e to the negative 1t. All right? Notice I haven't put a C1 or a C2 in there just yet, but we will in a second. I'm going to open bracket, put a closed bracket over here. This part pertains to what you get from the imaginary. This is going to be trig related. So watch carefully. I'm going to say C1 cosine of 2t. And again, that 2 is because we had a 2i. And we're going to say plus C2 sine 2t. And again, that 2 comes from the fact that our auxiliary is such a hard word to say. The root from our auxiliary equation was negative 1 plus or minus 2i. So here's the negative 1. It would be nice if I did this in color. Use some orange and blue here. Negative 1, because this was a negative 1. And this is a 2i. So that means this is going to be a 2. That looks nice. Make sense? Those are where those corresponding pieces go from the root of your auxiliary differential equation.
So, okay, so you don't have to do 2, even though that's plus or minus. You see negative 1 plus or minus 2i?
2i, right? Are you thinking there should be a minus here or something?
Yeah.
Really, remember, this C2 is like a constant, right?
Okay.
And it could be interpreted as a negative. And really, to be honest, this plus or minus has nothing to do. These are really just the solution to this equation. You don't actually interpret the plus or minus to be anything. All we care from this, all we want to glean from this equation, or this is the real part and the imaginary part. We don't care there's a plus or minus. Like, technically, the solution to this quadratic equation is this, but we're not trying to solve this equation purely. We want to solve this in an effort to get to this solution, which doesn't take into account the plus or minus. Cool? All right, so we're going to do a few more of those. We'll do 3 really quick. Come up with the top of my head. We'll do 2y prime minus, gotta have this works, 5y, oops, y double prime, minus 5y prime, minus 7y equals 0. So start by writing the auxiliary equation for that and start factoring it. I hope that factors. I'm pretty sure it does. It should. Yeah, okay, I think. Okay, you can just follow along as I go. So did you guys already factor this? What did you guys get when you factored it?
Oh, I didn't.
Good job. Okay, 2r and r. We're going to have the plus 1 here, but the minus 7 here. I think that checks out. You always want to check to make sure. Of course, it's really easy to check to make sure the first and the last match up. 2r times r is 2r squared. Negative 7 times 1 is negative 7. The middle term is what has to check out before you finally say, okay, we're good. 2r minus 7r is indeed negative 5r. So your roots are r equals 7 halves and r equals negative 1. So your solution will be y equals c1 e to the 7 halves t plus c2 e to the negative 1t, or just negative t. Yeah?
I just wasn't here, but like the r, so why do we use r?
Good question. Sorry. So this forms what's called your auxiliary equation. You're supposed to interpret this. You're converting this to what's called an auxiliary equation. We say 2r squared because we have 2 derivatives here.
Okay.
We see minus 5y prime, so we say minus 5r because we see 1 derivative here. How many derivatives do we see here? Well, we see none, so we say minus 7 because we have, you say 7,
okay.
0, r to the 0, but r to the 0 is.
And then
And this is all.
The r to the okay.
Yeah.
All right. Okay, so it's just like another way of just writing.
Yep.
Okay.
Well, we're converting this second order differential equation into an auxiliary equation as a way to help us solve it. Yeah. Cool. Now, this next one, Factors, how does that factor? If it was r, this is r squared minus 20r plus 100. I would factor how? Only got an hour here, guys. What are 2 factors of 100? What are some obvious factors of 100?
1 and 100.
That's very obvious, yeah. How about slightly less obvious?
5 and 20.
5 and 20? Sadly, don't add up to 20.
Mm-hmm.
What else?
Oh.
What are 2 factors of 100 that add up to 20?
Oh, 10
and 10.
Good job, Kevin.
And I'm doing this on purpose. I'm doing one with 2 distinct factors. I'm doing one with a double root. As you can probably guess, this is going to be one that's going to be complex, right? We'll get there in a second. So because we have a double root, we have our answer is y equals, well, I should have done this one in orange so you can connect the dots here. Y equals c1 e to the 10t plus c2 e to the, or c2t e to the 10t. Whenever there's a double root, you have to introduce this extra factor of t. Switch to green. How does this one factor? Well, it doesn't. If we start by writing r squared plus 45, which is the corresponding auxiliary equation, how would you solve that?
Quadratic form.
You could. Yeah, you could use the quadratic form if you wanted to. It's actually just easy to, there's no middle term r here, so you can actually subtract the 45 over and take the square root.
Oh, yeah.
That is, you would get r squared equals negative 45. And then what would you do? Take the square root of both sides, it gives you r equals plus or minus what?
Square root of 45?
It's 45. I root 45, yeah.
Yeah.
What perfect square does 45 have inside?
9.
A 9,
so
which is
3 squared of 5?
3 squares of 5, right. Not 45 has a factor of 9 in it. We can pull out as a 3, so we'll say 3i actually. And then if you pull a 9 out of 45, you're left with a 5, so 3i root 5. Notice, what's your real part here?
None.
0. There is a 0. You could have implied 0 there, so you won't expect any sort of e term. So your solution will be y equals, you could say,
C1.
e to the 0. I'm just writing for completeness, e to the 0t, because again, that's a 0, times c1 cosine of 3 root 5t. Actually, I'm going to say 3t root 5, just because I don't like 3t root 5. Running out of room here. Plus c2 sine of 3t root 5. Good? What are you confused about? Why is there not an I here? Maybe?
Also,
so here's my differential equation, starting here.
Yeah.
The corresponding auxiliary is r squared plus 45. Solve for r. The only roots I get are 0 plus or minus 3i root 5. The real part corresponds to the coefficient of t and the exponent of e. I'm using these terms that I know sound like jargon, but you actually know what these words mean, so make sure it makes sense to you. This 0 corresponds to the coefficient of t and the exponent of e, right? So I got a 0 here, that's the coefficient of t there. Cool? If it was 7, I'd put a 7 there. If it was negative 19, I'd put a negative 19 there. But it's 0, so it's got to be a 0 there, which is just, because we know 1,
so you
right?
can get rid of it.
Yeah, I can get rid of it. But I was writing it for completeness. The imaginary part, that is the part that is the coefficient of I, goes as the argument of the coefficient of t in the argument of cosine, and the coefficient of t in the argument of the sine here. Cool?
Okay. Because they're imaginary.
Right. Those are the imaginary, right? The imaginary parts correspond to the coefficients of t inside the sine and cosine. All right, and one more. Let's do this in black. I don't have any other colors to work with. We'll do red or purple, but no dice. This is, be very careful here. This is r squared minus r. How does that factor? If you were at home.
R. And
R
then
times
R minus 1.
R minus 1 equals 0. So my roots are r equals 0 and r equals 1. So my solution, y equals c1 e to the 0t plus c2 e to the 1t. Or you could just write it as c1 plus c2 e to the t.
All right.
That was not too small. Almost. Yeah, it's not just a little bit small, maybe. Yeah, what was that?
No.
Okay, cool. You can actually verify this. It's kind of weird because you got a constant, and usually all our all our constants C1 and C2 are attached to something that contains a T. Here's something that C1 times something that has a T in it. C1 times something that has a T in it. C2 times something that has a T in it. This is a C1 that doesn't have anything attached to it that has a T in it. But that shouldn't surprise us because we had a weird-looking auxiliary equation. Well, let's see if that makes sense. What happens when you take two derivatives of a constant?
0.
And what happens when you take one derivative of a constant?
0.
What's 0 minus 0?
0.
That checks out. Cool. And you can actually run these things through the differential equation to make sure they check out. Like, let's take C2 e to the t and plug it in. What are two derivatives of e to the t?
E to the t.
And what's one derivative of e to the t?
E to the t.
What's e to the t minus e to the t?
0.
It's magic. If I had shown you that these things actually work, you'd be impressed, but I don't have time to do that. You could take C1 e to the 7/2 t plus C2 e to the negative 1 t and run this through this differential equation, and you will get 0. It'll give you a huge giant mess, but everything will eventually drop out and cancel, which is great. Okay?
Yep.
All right. That's solving homogeneous.
So they really don't get any worse than that?
Nope. They get worse when you have the right-hand side as non-zero.
Okay.
But it's almost it's as easy as factoring. That's it. It's nice, right? We can talk about the method of undetermined coefficients, though I don't know if it's going to be on your exam.
I don't think so.
He covered it. You said he covered it today.
No.
You said you got to 4.4 though.
We ended at 4.3. So
Okay.
we didn't do that yet.
Okay, yeah. So we're not going to worry about it then. All right. So that's basically what chapter 4 is about. I want to briefly talk about mass spring systems.
Yeah.
This is an equation you're going to want to write down. My double prime plus by prime plus ky equals, we'll say fext. But again, because you haven't got to non-homogeneous differential equations, this guy is usually 0. It'll say usually 0 to start. Until you get to the 4.4, this will usually be 0. In fact, I'd venture a guess that this will always be 0 until after your first exam. So we're going to talk about what these letters mean, M, B, and K. And again, I've written it right inside the glare for the viewers at home. Sorry. M, as you probably guessed, may stand for mass. K is something you've seen in Physics 1. It's the spring constant, the stiffness. So we'll call it, you can either call it spring constant. The book will sometimes refer to this as the stiffness. They're used interchangeably. So you're going to be given a problem. A spring has a 3 kilogram mass attached to it, and the spring has a 10 Newton per meter spring constant or stiffness or whatever. And then this letter B. You know what this stands for? It stands for damping. Have you heard this term before?
No.
Damping. Okay. Damping is a object's resistance to oscillation. So, and this is a really cool example because we've got one in this room. I'm going to turn the camera to it. Right there. This guy. So I do it with my finger. No, my finger's just huge. That thing there. Right there. That's a dampener. I could just go fucking point to it. This thing. It's a damper. It's like a... If it didn't have a damper, what would happen? Well, the door would just go and slam shut. So we're going to do it quietly. See the resistance to oscillation?
Mm-hmm.
It's not, and if without the damper, it would just, well, have you ever seen like an old Western with saloon doors and the sheriff walks in and the saloon doors swing back and forth behind him, or you've ever been to a TGI Fridays and you see the kitchen door, it oscillates. There is no damping there. Or there is damping, it's just very small. It's what's considered underdamped because it's allowed to oscillate. That door didn't oscillate, right? It just kind of closed slowly. You might even consider that being overdamped because it's closed very slowly. So there's something called critically damped, underdamped, and overdamped. So we're not going to talk about that too much. Just give you an idea of what damping is. So you might be told a damping factor. If you're told what the damping factor is, it's telling you what B is. So what this does is if I said a mass of 3 kilograms with 10 Newton per meter spring stiffness or spring constant, say stiffness. Actually, that might not be. Let's not do that. Let's not do 10. Let's not even do. What would be good here? I'm trying to do this in my head here. Let's just do 1 kilogram. That makes things easy. Let's say 29 newtons per meter stiffness and 6. Kilograms per second. Remember let's say a damping factor of 6. of B equals 6. And then I'll say, find the equation of motion. So for those of you, if you can't read it at home because of the glare, a mass of 1 kilogram with a 29 Newton per meter stiffness, or K equals 29 essentially, and a damping factor of B equals 6 is released, or whatever. And that might give you initial conditions. We'll talk about that in a second. Find the equation of motion. All right. Well, we're told that the mass is 1 kilogram, so we have 1 y double prime, plus B is 6. We're told B is 6, and we're told the stiffness is 29. 29 is fucking awful. It's not even 29. 29 is bad. Can you change that to 25, please? Otherwise it's gonna be a disaster. Okay. Now we're set. Now we're set. Okay. 25 Newton per meter stiffness. So we're gonna say plus 25y. Because I didn't say anything about an external force, we're going to assume that there is none. So we're gonna say equals 0. And again, you probably won't have one until after exam 1, unless you happen to be doing 4.4. Some people are, some people aren't, I suppose. Anyway, this is basically the differential equation that governs the mass, the mass that's attached to the end of the spring. It governs the motion of that mass, All right, so we're going to write the auxiliary r squared plus 6r plus 25. It took me a while to finally figure out what numbers I wanted to use, but these numbers are such that it will not factor, sadly. So because it doesn't factor, if it doesn't factor, we're probably gonna think, hey, maybe I need to use completing the square. Maybe I want to complete the square to make this work. So we have, we're going to say r plus 3 squared, half of 6 is 3, equals negative 25. What am I missing?
Plus 9.
Plus 9. This is a 3. I need to square that. That means I need to put a plus 9 on the right-hand side. That's how you complete the square there. So we have r plus 3 squared equals negative 25 plus 9 is negative 16. I want you to solve for r now. That gives me r plus 3 equals, what's the square root of negative 16?
4i.
4i. And then subtract the 3 over to give me r equals negative 3 plus or minus 4i. 4i's. Right? Stop calling me that. Okay. What does that mean the equation of motion is? Now, we'll get y equals, and again, let me write this in negative 3. Write this in orange. 4i. So we have y equals e to the
negative 3.
Open bracket, c1 cosine of 4t plus c2 sine of 4t. So that's your equation of motion that governs the... oh, by the way, you can see that it's stamped here. What kind of exponential is this? What is this guy going to do as t gets larger and larger?
Go to 0.
So what kind of exponential? It's not a growing one, it's a...
Decreasing.
decreasing. I used a different term for it last time. A decaying exponential.
Okay.
So a decaying exponential looks like this, and on the other side it will look like this. You don't have to draw it. But notice that because it's got some cosines and sines, what's it also doing? What does cosine and sine tend to do graphically? Starts with an O?
Oscillate.
Oscillate. So here's what the equation of motion looks like.
Okay.
The saloon door situation is going out, in, out, in, out, in, out, in, out, in, out. Cool. Till it stops, right? Okay. Good.
Mm-hmm.
You might be given some initial conditions in the following way. They might tell you the object. They might say the object is stretched to an initial. They won't even say the initial position. They won't give it away like that. So they'll say the object is stretched to 1 meter from equilibrium. If the object is stretched 1 meter from equilibrium, that's implying that y of 0 equals 1. We usually tend to take a stretch to be a positive displacement, and a compression is a negative displacement. So if I said the object was compressed 2 meters from equilibrium, you would say y of 0 equals negative 2. Make sense? So this is a stretch, meaning you have a positive displacement. If we said compression, then it would imply a negative displacement. Also, when you stretch a spring, I can have a spring here. I could stretch it to the right, or I guess let's put it here. I always think of this as the positive direction, right? I'm making sure that works for the camera too. That's the positive direction. So when I stretch it to the right, it's gonna take out that positive direction. So they also might say stretch to the right, or or they'll say stretched, I'm sure. Anyway, stretch is positive. So I stretch to the right, and I say something like release in such a way that I give it a velocity to the left. I might say the block is released in such a way as to give it a velocity of 2 meters per second to the left, so this way. So that would say y prime of 0 equals -2. And let me repeat that sentence. You can write it down if you'd like. The object is released in such a way so that it has a velocity of 2 meters to the left. And again, for most of these problems, we tend to take the convention is to have that kind of setup where we have a wall on the left and the block is on the right. Equilibrium is here, and if we stretch, it's stretching to the right. If we talk about velocity moving to the right, it's in the positive direction. Any movement in the left direction is considered negative movement, negative velocity. Good? All right, I think we've covered spring. This will help you find C1 and C2. By the way, this is kind of a pain in the ass to have to do, but what's y0 of 1 mean? It means you plug in 0 for t and you let y equal 1. Well, what's e to the 0?
1.
What's cosine of 0?
1.
Mm-hmm. What's sine of 0?
0.
So what do we have here? We have 1 times C1 plus 0 equals 1, right? So basically, this is giving you C1 for free. Because again, when I plug in 0 here, I get 0. When I plug in 0 here, I get 1. Or sorry, I get 1. Yeah. And when I plug in 0 here, I get 1. When I plug in 0 here, what do I get?
0.
0. So I'm just left with what?
C1.
C1, and it equals whatever number I have here. Sadly, the y prime is going to be a pain because you have to take a derivative of e to the something times a cosine plus sine. Well, don't distribute this e to the t through because you have a product rule. E to the t times a cosine plus sine to do one product rule. I've seen people do this. If you distribute the e to the t or whatever you have to the cosine of the sine, what are you going to have? You're going to have an et cosine and an et sine. What do you have to do to take the derivative of et cosine?
Product rule.
What do you have to do to take the derivative of et sine?
Product rule.
So you have to do two product rules because you decided to distribute the e to the t. So don't do that. Save yourself the time and just do one product rule. Okay? All right, that's enough about springs. So we got about 23 minutes left. 20 minutes left. We're good. What else do we want to talk about? We can go back to first order differential.